Hello guys and welcome back. Here is another problem about forces and Newton's law. The problem is called scale in an elevator. So let's start. A child places a bathroom scale on the elevator floor and stands on it. When the elevator is stationary, the reading of the scale is 45 kilogram. When the elevator starts moving, the reading of the scale drops to 39 kilogram. So we have a child, she's standing on a scale inside the elevator cabinet. When the elevator is stationary, there is nothing moving, then the reading of the elevator, of the scale is 45 kilogram. While when the elevator starts moving at the beginning of the movement, the reading of the scale changes and it reads 39 kilogram. So the question is, find the magnitude and the direction of the elevator's acceleration at that moment. So we want to find, or we are looking for, the elevator's acceleration. Now logically, since we are asked about the elevator's acceleration, logically we think of applying Newton's law to the elevator. But that's not possible because we don't know all the interactions of the elevator. The elevator has a rope that is holding it by tension. The engine is working somehow. There might be frictions with the wall. The scale itself pushes the elevator. So there are a lot of interactions of the elevators we don't know. So we cannot actually apply Newton's law directly to the elevator. However, we can see that when the elevator moves, the child inside the elevator is going to move with the elevator. So the child's acceleration is equal at any time to the elevator's acceleration. So if we are able to find the child's acceleration, and it's much easier for us to study the child, we know what is the elevator acceleration. Also, before we start applying Newton's law, we need to understand the reading of the scale. Where does these numbers come from and what do they mean for us? The scale doesn't measure mass directly. It measures it through the force exerted by the child on the scale. So when we stand on the scale, we push down on the scale. And this pushing down, there might be a spring or something in the scale that varies or has a scale on it. And it gives us the reading in kilogram. So basically the scale is calibrated to read the force that the child exerts on the scale divided by the gravitational acceleration g, and it would give us the reading directly in kilogram. So from the reading of the scale, we can tell what is the force that the child is exerting on the scale. But we also know that the force that the child exerts on the scale is equivalent to the force that the scale or the floor exerts on the child. And that's equivalent to the normal reaction that the floor exerts on the child. So we from the reading of the scale, we can tell what is the force exerted by the ground or the floor, the elevator floor on the child. So now we can start applying Newton's law. Let's simplify our figure. So now we have our child is represented by this blue box, and the object we are studying is the child. Now, so the second step after identifying the object that we are studying is to look at the forces acting on this object, the interactions of this object. So for the child, we only have two interactions. We have the weight, vertical downward, and we have the normal reaction, vertical upward. It doesn't matter if this elevator is moving or accelerating or not. That's the only thing that is interacting with the child. So basically what should provide the acceleration for us is the combination of weight and normal reaction. After that, we choose our axes. Both forces are vertical, and if the elevator is going to move, it's going to move up or down. So we choose the y-axis, vertical up. Then we write Newton's second law. So Newton's second law tells me that the weight plus the normal reaction is equal to the mass of the child multiplied by the acceleration of the child. We have one axis, so project on this axis on the y direction. Weight is downward, so it's negative, it's minus mg, plus n equal to MAY. We also remember that the normal reaction is equal to the reading of the scale times G. So in the first situation where the elevator was stationary, we know that the acceleration is 0. We are stationary. There is no acceleration, neither up nor down nor any kind of motion. So when we replace that back in the projection of the Newton's law, we got mg equal to n. So the reading of the elevator, which is n over g, we can replace it over here, and g cancels out, and we got m equal to the reading, and it's 45 kilograms. That's the normal situation. When we stand on the scale, the reading should be equal to our mass. However, when the scale, the elevator starts accelerating, the child is accelerating with the scale. So we have an acceleration, it's not 0. And that's what actually we want to know. But before we write the equation for the acceleration, let's actually analyze the situation a little bit. So if we write n in terms of m and the acceleration, n is equal to m into g plus ay. So it's not anymore mg, it's mg plus, m into g plus the acceleration ay. So what does that mean? If the child and the elevator are accelerating upward, so the acceleration is positive, then n is going to be larger than mg. So n, normal force, is going to be larger than the weight. So that would provide the upward acceleration. So the floor is going to start moving up and it pushes the child with it. So in this case, the reading is going to be larger than m. The other case is that the acceleration is negative. If the acceleration is negative, then n is going to be less than mg. So it means that the weight is going to pull us down because there is no enough normal reaction to opposes the weight. And in this case, the reading is going to be less than m. The extreme case of this is when the acceleration is equal to minus g. That's the free fall case. So if we disconnect the elevator and the whole shaft, the whole cabinet starts falling with an acceleration is in magnitude equal to g, it's minus g because it's downward and we chose the y-axis upward, then the normal reaction is going to be 0 and the reading is going to become 0. So when we are free falling, the weight doesn't allow us to push on the ground, so the ground doesn't push back on us. Now let's find the acceleration. So we know that in this case, when we are accelerating, the reading is 39 kilogram. This is less than m. So we are in this situation, in the second situation. So the acceleration, we know that the acceleration is negative. We rearrange this equation. We replace what is n, and we got that the acceleration is equal to g into minus 1 plus the reading over m. So we divide the reading of the current reading of the scale by the mass of the child. So when we replace these numbers, we got a negative number, obviously. It's minus 0.133 g. And in meter per second squared, it's minus 1.3 meter per second squared. So the elevator is accelerating downward. But accelerating downward doesn't mean that we are moving downward always. In general, if we have a negative acceleration, this could mean that we are moving downward and speeding up, or we could move upward and slow down. Here in this case, because they mentioned that we are starting to move, so that means that we are moving down and speeding up. But when we reach, for example, if we're going up and we reach the top floor, when you are stopping, this could also result in a downward acceleration or a negative acceleration on the y-axis. Thank you.